This is the lesson from September 19th, 2017, and this lesson is on the relationship between solar radiation and temperature. Okay, so today's objective. Students will be able to use graphs to explain how average temperature varies latitudinally with light intensity on Earth's surface. So we're going to write in our objective. And so this is what we do every day in class. So we do our do now, but we also fill in our daily objective. It's important to know what the learning goal is at the end of each class. And so today we will use graphs. So this is how we're going to learn our new material. And we're going to be able to explain how the temperature varies across latitudes. And so those horizontal lines on the globe, that includes 0 degrees. This is the equator. That is a line of latitude. And so our do now questions. As you travel farther south, how does the temperature change? So these questions are setting us up to either prime our knowledge that we have prior to coming to class, tap into yesterday's lesson and review a little bit, and sometimes we do some kind of predicting or guessing in case we don't know. Okay, so as you travel farther south, to qualify this from where we are now. So from Delaware to say Florida, how does the temperature change? And we would say that the temperature increases. And now I'm abbreviating here, and it's okay for us to abbreviate during the do now. Anything that's notes for our own sake, something that we understand ourselves, it's fine to do incomplete sentences or abbreviations for something quick like this. However, when we're turning work in or I'm asking for complete sentences, we want to make sure that we write this in a complete sentence. Why doesn't as much light strike at the poles? So this is something going back to yesterday's lesson from September 18th, Monday. And so we have our globe here. We have our lines of latitude. We have our axis, our tilted axis of the Earth. And so the sun's rays are coming in from over here. As they hit this part of the globe, if we take a closer view of this, it's like a flashlight being shown over a larger area here, versus at the poles, you get the direct sunlight. So this is direct, and this is glancing is what this is called. And so when we have direct sunlight hitting the center or the fattest part of the Earth, that's going to give us more sunlight. So because of the curve of the Earth. And so our answer for this one would be because of the Earth's spherical shape. Why do we have seasons where we live? And this one was a stretch question, something to use the knowledge you might have already had and even make you think a little bit more critically. And so we have seasons because of the tilt of Earth. And like I said, for question 2, our axis is tilted by 23.5 degrees. And so that tilt being either farther away from the sun, or if it were over here, it'd be closer to the sun, gives us our seasons. Okay, and so this diagram is showing you a much better representation of what I attempted to draw on the last slide. And so these are simplified beams of light, and normally we would think of light as not these individual beams, but kind of just like a curtain of light shining towards us, just bathing the whole Earth, and we're kind of just in the path of it. And so these beams of light are a simplification, but it's a good idea of what happens once it hits Earth. So all of these are the same size. And you can tell because all of these circles, and that was terrible, so all of these circles are approximately the same size, right? So this one, they're all the same size. As they approach Earth, it depends on where they hit the sphere. And on any sphere, it's dimmer up towards the top and bottom, and it's brighter here. And so as scientists, we're observing the different ways that light interacts with this shape. And so it seems very simple to notice how light interacts with the shape. But when we're thinking about something as large as the Earth and something as powerful as the sun's rays, it actually has a really big impact on life here on Earth. And so because of this brighter light, it's more direct. And as our activity down here asks us to do, write the words most intense next to the beams that strike the globe directly. And then write least intense in the locations where the sunlight strikes the globe at an angle. So our light will be least intense at the poles. And I'm just going to abbreviate here, least intense, Li. And then these middle beams will be most intense. And this one's probably like the middle. So this one's kind of at an angle. It's a little bit larger of an area than these circles. And if this is still kind of abstract for us to think about, the analogy I used was a tablespoon of peanut butter. If you take the tablespoon of peanut butter and put it on a slice of bread all in one spot, that's a lot of peanut butter that you're getting in one bite, right? So it tastes like all peanut butter. However, if you take that tablespoon of peanut butter, it's the same amount, but you spread it out over the piece of bread, it's going to taste a lot less like peanut butter. It's going to be less intense. And so I think of that in terms of this light. In these spots, all that peanut butter, all that light is landing right here, and it's not really spreading out a whole bunch. And so it's really intense here. However, at the top and bottom of the Earth, it actually spreads out a lot more, and so there's not as much light there. And because of that, it is colder, because there's more light spreading out over a larger area. So it's not as intense, and it's, as a result, colder. This is another graph showing very similar data. So here we have net radiation. And net radiation means that we take into account the albedo of Earth. And albedo was one of our vocabulary words that we learned yesterday. And so we say minus the albedo. And if we remember the definition for albedo, that is anything that's reflecting off of the surface. So we're subtracting the reflection off of the surface. So our reflection might be off of trees or the surface or clouds. In this diagram, this is a satellite image of Earth. Around the center here, we see is the most orangey red color. And we see that with net radiation, so the amount of sunlight, the more orangey red it is, the higher the light intensity. And so this is more light around this center area. And then as we see here at the poles, it's bluish color. But anything below this like bright white is a 0. How do we have a negative radiation? How do we have radiation that's not even existing? Is that what that means? Well, actually, what it means is that this radiation here is either being reflected or absorbed. It can be absorbed by trees or any kind of vegetation. It can be reflected, especially here at the poles. What do we know is at the poles covering the top and bottom of the Earth? Ice. Ice is a very big factor in the albedo of Earth and the reflection of sunlight. And when we're going to learn later during our global climate change talk is that the ice levels that are disappearing and kind of shrinking over time are causing even more warming of the Earth because a lot less light is being reflected off of these ice sheets. Now we'll look at this graph here on the left, and this is just one more way for us to see the same type of data. So I want you guys to see that there are many different ways that we can show the same information, but as scientists we are able to interpret this information no matter what form it's given to us in. So we see net radiation here. Average insolation. This is a whole nother way of saying radiation. This is the amount of sunlight reaching Earth. And so But this is kind of a strange graph. It's flipped on its side. And for one, I intentionally did that. However, because I wanted to line up the equator with this image here. And so we imagine the Earth on this, where we had the equator straight in the middle. And so I put the equator here because this axis is showing us latitude. And this is 0 degrees latitude, which corresponds to the equator. And if we look, right at the equator, that's where this graph reaches its highest number of 10, because then it goes 8, 6, 4, 2, 1, or 2, 0. And so when our latitude reaches 0, our insolation, or the amount of sunlight, reaches its peak, or its highest point. And so that corresponds to this graph, where that is where the most intense light is being shown here. Now on to our main objective of the day. We're going to be using these graphs to determine that the average temperatures of the Earth vary with sunlight. So first thing, we're going to identify the continents that are being evaluated here. These black dots indicate and so we're going to use our graphs to determine how temperature is varying with latitude. And so first we're going to identify these continents. This station, this monitoring station, is in Peru, and that is in South America. We're going to go back to our graph in a little bit and put these on the world map, and we're going to see where all these stations lie and how temperature is varying. This next one is in Liberia, that's in Africa. So we'll write Africa right here. And in Africa, our station here is measuring this data, and we're going to talk about this in just a second. Finally, we have Australia, so we don't need to kind of pick it out from a country, so this is Australia, an entire continent. Looking at these graphs, we see a couple of things. First, we see this red line here. This is the temperature line. The red line here, not the black line. And then we have precipitation. And so we have that here, but it's a little bit small, so we know that these are precipitation bars. The higher it is, the more precipitation. And so if we look, which axis do we use? We use the one that says temperature above it. And we're going to be looking at the temperature of all of these graphs. I have placed a black arrow pointing from approximately what the mean or the average temperature is at each location. You can see they get kind of squiggly because of the seasonality of the temperature in some of these places. But on average, this is what the temperature turns out to be. So starting with South America in Peru, our line points about to, I'd say that's about 25 degrees Celsius. And we're not going to be using Fahrenheit because most of the world uses Celsius, and we want to practice being citizens who can use Celsius in the metric system. What your task is for the class is to go through the next 5 graphs and determine the average temperature, write them below each graph, and then I have some follow-up questions for you. So if you would like to do that and you have the packet, please do so, pause the video, and come back to us. Alright, so now we're going to do these together. For Africa, our line points to, I'd say that's about 28 degrees Celsius, and we always want to include the units for any measurement that we take, because otherwise we don't know what we're measuring in. This one is probably maybe a little higher, probably 29 degrees Celsius, and I'm getting a little close to my video here, so I'll just put it up here, my little Celsius. Okay, so we have 25, 28, and 29. Okay, now we move on to our next 3 graphs here, and we're looking here first at China. At China, here's our station, and our average temperature is probably about 22 degrees Celsius. Now looking over to Alaska, here's our station here, and just for reference, we're probably right around here. That's kind of where Delaware is. And so we're over here, here's Alaska, so it's quite a bit far north. And this is around 9 degrees Celsius. And so we're at South Africa, and so we're probably close to the Antarctic Circle down here. And this average temperature, not quite at 20, we're probably at about 19 degrees Celsius. Okay, so my follow-up questions are, looking at the temperatures for these three, we had 28, 29, and right around 25. So we're going to put these locations on this map here and see where they kind of end up. So we have, our first one was in South America, so that's where A was. B was right here, and C was up at the north of Australia. And then we had D was in China, E was in Alaska, and then F was down here in South Africa. So my question for you is, what pattern do you notice with the first three locations? Where are they located on the map, and what are their temperatures looking like in comparison to the latter three, or the second set of three, D, E, and F? If you compare those temperatures between the first three and the second three graphs, what do you notice? What I would like you to find from this is that A, B, and C, A and B are here, here's C, very close to the equator. And D, E, and F are farther from the equator. And what we see was the range from the first three are 25 to 29 degrees Celsius, and these range from 9 to 22 degrees Celsius. So we now see from data at actual climate stations measuring temperature that the average temperature of the locations closer to the equator are higher than those farther away. Finally, I would like you to predict what a graph of temperature and latitude would look like. So let's go back to our light versus latitude graph. So this is the amount of light coming in, and the latitude. Our graph is going to look very similar. So to set up our graph, and I'll get you there first, then you can pause it and see if you can predict it on your own. We put 0 degrees latitude here. If you remember, that's called the equator. And then we have 30 degrees, and these are very important degrees latitude that we're going to talk about in the future. So 30 degrees and 60 degrees. And these repeat above and below the equator. So here's our equator here. And then finally, please label the axis, the vertical axis, also known as the y-axis, in 5. Okay, so now we have our vertical axis labeled and with the title and the units. And we have our horizontal title, and the units are degrees. At this time, please predict what the temperature versus latitude relationship would be. When we're graphing anything, that is a relationship that we're looking at. So I'm going to give you time to do that. You may pause me and then come back to me when you're ready. Okay, welcome back. So we're going to look at what the relationship should look like, and then I want to see if you were close. If you weren't close, then what happened, and we can figure it out, and then we understand why it is the way it is. Okay, so I always like to start with the equator. I know that this is going to be, has the most sunlight, and it's the widest part of the earth. It's closest to the sun. So in theory, it should be the warmest. So it should be about somewhere around 40 degrees Celsius on average during the year. And that might be even a little bit high, but that's pretty close to what it would be. Going 30 degrees above or below the equator, it's going to be very warm, but it's not going to be as warm. 30 degrees latitude, we find a lot of deserts, so it still gets very hot. 60 degrees, this is the poles, and this may average closer to around maybe 10 degrees. And where we live, Delaware, is probably somewhere 30, let's say somewhere around here, Delaware. And so we would be somewhere in this range, 20 to 25 degree range, maybe a little bit higher. So if we draw some lines here, connect this graph, and this is a little bit wonky, but that's okay. We're just predicting here and making a guess at our relationship. But our relationship should be something like this. It should be highest at the equator, temperature decreases towards the poles. And it should have a very similar relationship to our light relationship here. Okay, that's today's lesson. Hopefully you learned a lot about how solar radiation increases the temperature on the surface of Earth. And in the next lesson, we'll talk about how solar radiation and temperature translate into precipitation patterns on Earth and cause convection cells. If you have any questions or comments or feedback, please email me at schultzscience@gmail.com. My students, you also know my school email. Feel free to send me an email there or ask me a question in class. Thanks, and I'll see you next time.